So, welcome to my dear students and learner. So, basically, this video also a requested video where some people they specifically ask um, to know about the uh, tuning process to for a field oriented control. Basically, it is for um, very oftenly it is called as this variable frequency drive VFD. So any prime mover like coolant control or any kind of application, pump, fan, blowers, um, all these things. Some nowadays that electric vehicle applications, EOT cranes, everywhere um, in locomotives also. They are basically this kind of variable frequency drives are there. Um, so I'll give you just a brief history of that. If you go early, middle of um, uh, uh, or you can tell early 1900s. So when the speed control was concerned, people are very oftenly used this internal combustion engines. Okay, it's very the governing system is pretty simpler. Means by controlling the fuel injection or fuel supply, you can control the speed of the engine, like our car. That throttling directly, it is uh, controlling the fuel injection or the fuel supply in the combustion chamber. But one problem is there that the I can give you an example. Say you are driving your bike in a very smooth highway, like say your Navi Mumbai road, which is going Mumbai to Pune, or that Lonavala Khopoli that side. So there, the road is very wide, smooth, and you can drive your car in fifth gear or ride your bike in fifth gear, something like that, because the torque requirement is very low comparatively. But rather, instead of that, if you are riding your bike or driving your car in a very bumpy road, a village road, broken road, where the torque requirement is high, you cannot ride your bike or drive your car in fifth gear. Definitely, you have to come down to um, uh, first gear or second gear, like that, because um, uh, your wheel driving wheel shaft required higher torque, and as the power is constant, so to mitigate that, you have to bring down the engine shaft speed. What I mean to say, this in an for an internal combustion engine, the torque and RPMs, or any rotating machinery also, this torque, basically power is basically the product of torque and RPM. So definitely you have to bring down the um, uh, RPM to elevate the torque, and vice versa. But when the DC machine evolved or invented, DC electrical machines or DC motor, specifically the separately excited DC motor. So you can think that there is a two galvanically isolated circuitry. One is for armature control and another is for field control. So by controlling the armature current or armature electrical parameter, you can control the speed, sorry, torque. And if you see the equation also, okay, and by controlling the field circuit, you can control the RPM. What I mean, this is called decoupled control. Even though torque and RPMs are very tightly coupled with each other, but in a separately excited DC machine, you will be able to control the torque and RPM in an isolated manner. Okay, but the problem is, even though till 1980, still today also few old industries like some steel industries, paper mills, uh, such some refineries also, uh, it is a non-safety area. So people are using this separately excited DC machines because the decoupled control is very easy. Hmm. But the core refinery area, the hazardous area, the nuclear sectors, there we can't use a DC machine. There are certain disadvantage. In DC machine is operating in the rotating, there is a brush commutator sliding contact mechanism. So in case of higher power, when the power is transferring through the means high current is flowing through a sliding contact, there is a possibility of spark. It cannot operate in an hazardous environment like pharmaceuticals, chemical industries, nuclear sector. Okay, there it is refineries. It's not possible. And moreover, the it needs periodical maintenance. You need to change the brush and commutator periodically. And main thing, the DC machine is costly. You can tell overall this not a robust design. So when in India the first induction machine came into the market, I think that is why through in India it is introduced by Kirloskar. So it is a very robust design and it is much more economic. No need periodical maintenance. It can operate very nicely in hazardous environment. But the problem what now people are facing, that is, in separately excited DC machine, you operate the machine as torque and RPM control in an isolated manner. But in AC machine, it is not possible. You can take one example, say our ceiling fan. This ceiling fan is an induction machine. So for a certain instant, it is operating. Say our terminal voltage is 230 volt. It is the current is drawn by the fan is say 2 ampere, for example. This 2 ampere, when it is going from electrical domain to mechanical domain, uh, this is generating basically the torque and RPM. Now, can anybody tell that how much ampere from the 2 ampere, how much ampere is responsible for torque production and how much is producing the RPM? No, it is never possible because it is depend on the so many other factors like the rotor position, because it is an asynchronous machine. The entire the armature or the rotor is getting magnetized due to the induction uh, which is taking place from the stator. There is no electrical connection in between, so it is very difficult. And this, the current component for torque and the current component for RPM is a vector summation. It is a vector, you have to split, it's a vector. Total current is the vector summation of that. So angle is a magnitude is not enough. You need to know the angle. Where is the rotor flux? From there only you have to understand. You have to, once you can able to achieve that, then you can operate an induction machine uh, analogous to a separately excited DC machine. That means at any RPM, the machine will be capable to deliver the full torque to the driven equipment. So this is achieved. The control, now the job of a chemical engineer or the control engineer become very tricky. How to do that? The you have to align the instantaneous rotor flux with the direct axis of synchronous rotating reference frame. So first, I think people who are electrical or chemical engineer, they know very well that first stationary axis to rotating axis. Okay, that means your ABC to alpha beta. Then from this alpha beta means the three phase to two phase transform. Huh. So you have to convert that three phase current to two phase current, because why? My target is to operate the induction machine, three phase machine, analogous to a separately excited DC machine, where the main current component is armature current and the field current. So there are two phase. So first I will convert this three phase to two phase. Now the rotor is rotating. That stationary phasor, now it will produce the uh, torque and RPM in the rotor. So you need to, that is rotating. So this alpha beta, again you transfer another rotating reference frame, which is called alpha beta to DQ transform. This, when you are transforming theta, the angle is a very important factor. So to know the instantaneous rotor flux angle, you need to do all these things. Now the question is, it's a very brief subject, and this is my regular subject in several educational institutions also. Now if you see, I'm not going into the details because without mathematics it is not possible to explain. So this is a control system. Now you see this top line, there two PI regulator, this one and this one, and in the bottom this is D axis, this is D axis, and this is Q axis, and the entire dynamic performance of the system or the motor, how it will operate, it is depend on these three PI regulators, two in quadrature axis loop and one is D axis loop. Another problem is, this RPM. So this this outer quadrature loop, this is called the speed loop, and the inner quadrature loop, it is called the torque loop, and D axis loop is called basically the flux loop. Now another problem is, this RPM means flow, or RPM, heat, temperature, all these things are very slow process. That means, say suddenly in a room, if I increase the enthalpy in an impulsive manner, the temperature will not increase that much faster. It will take some time. Similarly, if you increase the RPM of an pump, immediately flow will not that increased flow will not reflect immediately. It will take some time because it's a very slow process. So in that aspect, your here the RPM loop, or this loop, is the sluggiest loop with a natural frequency of 1 Hertz. Then the faster loop is this flux loop, which is um, operating at a natural frequency of 10 Hertz. And the fastest loop is this torque loop, which having the natural frequency of 100 Hertz. Now you can think, then if you conceptualize the Bode plot, or the Nyquist plot, the three systems are coupled together with different natural frequency, and they are dancing with in different phase plane. How difficult it is. So exactly, the dynamic performance of the machine is depend on the perfect tuning of these three PI regulators. So far in my till today, in it is very easy for low inertia machine and low voltage machine, but in medium voltage or high voltage machine, uh, when the capacity is more than a megawatt, it's a very tricky. The auto tuning will not work. Again, I am repeating, the auto tuning will not work. You will not get that much good response from the system. Like, you can tell that in steady state everything is normal. Now you can see, now it is late night, it is around 1:30. I am very relaxed mood. uh, so my I will behave with you very gently. That steady state control, I mean to say, the steady state control is not at all an issue. To handle the transient is the question. If I am excited state, without anything I will shout somebody. That will actual my behavior is will exhibit from there only. In an you can recall our 12th class mathematics, second volume. How we will solve a differential equation, ordinary differential equation. First, you will uh, consider the excitation is 0, that right hand side is 0. By doing that, you uh, establish the auxiliary equation, find out the root, and that will be exponential of that root. Hmm. Another is, you consider the excitation. This is without excitation, the solution whatever you are getting, that is called the complementary function, and then you have to calculate the particular integral, and both club together, and it will give the instantaneous output. So this complementary function is the transient response of the system, and this uh, particular integral, that is the steady state response. This steady state, very nowadays you see people are going for dating. Definitely this is very much relevant with this. You cannot understand these things. A boy cannot understand a girl, or a girl cannot understand a boy within 1 or 2 days. They're going, spending time, try to identify the system, I mean to say. They are trying to identify or model each other so that in later they can behave accordingly, so that the life will be very smooth. And the transient, a boy can handle a girl's transient, and a girl can handle a boy's transient. So this is basically to improve the dynamic response in your life. Similarly, to here also, that is very much important. But how to know? For the tuning, first you have to know the transfer function. Then you have to linearize it. Then you have to tune it. Unless otherwise a system is not getting linearized, you cannot tune. And even though you can tuning also, it will not give the better dynamic response. So the first thing, definitely you should have, you must have, not should have, you must have an idea about the all loops. So um, I will tell you and I will not extend the lecture, because this is a very introductory things. In depth, if you want, I will uh, uh, ready to explain the things, but that will be full of mathematics. So first, to establish a transfer function, what you need to know, you need to know the input and output of a particular system. So in the speed loop, what is the output? The output is the RPM, and this RPM, from where it is coming? Torque is there, RPM is there. So now it is very clear that in the speed loop, the output is RPM and the input is torque. Now coming to the flux loop. Flux is for what? It is basically producing the magnetization to the rotor. And where it is coming? It is coming from the magnetization component. So, which is the Basically, the steady state stator direct axis current is called the magnetization current of the motor. People who are electrical engineer, they can understand my statement. So for the flux loop, your output is basically the magnetization or the flux or the magnetization current, and the input is stator direct axis current. Correct? Now coming to the torque loop. Torque is coming from where? Armature current. So in that transformation system, or in this frame of reference, the armature current is the stator quadrature axis component. And when the current is concerned, where it is coming? It is coming from the stator quadrature axis voltage. So now I am summarizing. For the speed loop, the output is RPM and the input is the torque. And for the flux loop, the output is the magnetization current and the input is the stator direct axis current. And for the torque loop, your output is the stator quadrature axis component and the input is stator quadrature axis voltage. So with this, basically, as I was telling that till today I have tuned nearly 40 medium voltage drives all over the country. So while we are going to do this, the first job I do this the no load run. The passive parameters like motor, stator and rotor, inductance, resistance, all these things, it will be coming from the motor design data, means motor data sheet. After this, we will do a no load run and we will capture all these input and outputs. Okay. After that, there is a very good tool available in MATLAB which is called system identification tool. With that system identification tool, I will estimate the transfer function of this 3 loop, and then very easily I can tune it. So for medium voltage drive, once the tuning is concerned, you have to know the control loop inside the control system. You have to find out what are the input and output of each loop. Then you have to do the motor. You have to take a no load run for the motor and capture those parameters with definitely the sampling time should be the lesser than or equal to, at most it should be equal to the switching frequency of the inverter. Then with the help of system identification tool in Simulink or MATLAB, you can predict the transfer function and then easily you can tune the system. This is a very brief idea about the tuning of an induction motor when it is operating in field oriented control mode or vector control mode. If you want to know further exactly, I can give you an example also. In my lab I can simulate one motor and capture the data how, and then it will be very clear to you. You can write to me in the comment section with your identity and contact details. Definitely I will do till my knowledge, and I will try my level best that the concept is clear to you. Now it is late night, around 1:45, so I have to take rest. So hope you have understood and learned something. Thank you so much. Thanks for your patience.